Now we are going to discuss about a capacitor. How does a capacitor function when a voltage is applied, and the mathematical equation of a current through a capacitor and the voltage across of a capacitor. And also we're going to see the energy stored in a capacitor mathematical formula. A capacitor is a passive element and it stores the energy in the form of electric field between the plates. We know that it consists of two plates separated by a dielectric medium, or we call it as an insulating material. If you look at the symbol of a capacitor, it consists of two plates as shown here. And these plates are separated by a insulating material. If a voltage is applied for a capacitor, or suppose then a current flows through the capacitor. Let the capacitor is having a capacitance C and a charge Q. Then the current through the capacitor can be given as rate of change of charge. Is nothing but rate of change of charge. The amount of charge developed across the capacitor is directly proportional to the applied voltage here. If I remove this proportionality constant, I can equate it as V equal to C into V. I'll make it as equation 2. And this as equation 1. Where C is nothing but capacitance parameter of the conductors. If I substitute equation 2 in 1, therefore we get current as I equal to d by dt of Q is nothing but C into V. As C is a constant, I can keep beside from the differentiation. Therefore, I get dV by dt. So this is the current equation through the capacitor. From here, I can find out the voltage across a capacitor. Just apply the integration on both sides. Therefore, I get V here as 1 by C integral minus infinity to t I dt. Here the limits we are taking from minus infinity to t because the property of the capacitor is it could able to store the energy. So for example, if previously that particular capacitor used by someone, then it might all store that energy. So to get the previous energy stored, the limit is here mentioned from minus infinity till the present time t. And power is given as we know that power is nothing but product of voltage and time. So we can simply substitute the value of V and I so that we can get the power. Now we are going to see the energy stored in capacitor. We know that energy is nothing but integral of power. So we know that power is V into I dt, where V is nothing but I'm just gonna write it as a V, and I is nothing but C into dV by dt. I just substituted here the current value into dt. Dt will get cancelled. We know that integral x dx is nothing but x squared by 2. Similarly, integral v dv is nothing but v squared by 2, and c is a constant. So that will get half c square. This is the energy stored in a capacitor, mathematical formula. Now we'll see the charge versus voltage characteristics of the capacitor. How does it vary? QV characteristic we say. QV characteristics. So on x-axis, I'm taking voltage, and y-axis charge. If you look the relation between these two, the characteristics would be like this. At any point, if you take, the slope is going to be same, and that is nothing but the capacitance. Capacitance is nothing but Q by V. We know that Q is nothing but C into V. So from the characteristics, QV characteristics, we can say that the capacitor is a linear element and it is a bilateral, because I could say that it could offer the same impedance for either direction of the current, so that it is a bilateral. And also, if you look at the characteristics, it is not changing with the time, so that I can say that it is time invariant in QV plane. And also, we know that the capacitor is a passive element.